can see, there's certain language to communicate different components of an equation, such as variables. And then constants are numbers that have fixed values. So when you're talking about just normal numbers, you can say constants. And there's coefficients, operators. Terms are sections, parts of the equation separated by operators. So like 3x and 2. Expressions would be combinations of terms and operators. Then there are equations in which you have an equal sign here. So that's the difference between an expression and an equation.
I see.
Yeah, and then there's inequalities, functions, exponents, radicals, integral and differential operators. You're not really working with these currently, but you will as you progress. So
I've worked with exponents.
Yeah, of course, yeah, exponents. But then some of these you'll get into.
Integral and differential operators.
You know what? I'm not entirely sure. So, yeah, that's just while you're communicating, it'd be instead of calling them thingies.
Yeah.
It'd be good to know what they're
yes,
called.
Thank you.
Yes, no problem.
You see, this is why I needed to do the presentation, or else
Yeah,
I would not have been clear on all the things that I messed up on.
that's true.
Partly because I was distracted.
Yeah.
And also because I wouldn't have learned all of that stuff. I actually only learned that those signs were called operators while I was prepping for this presentation.
Nice.
So,
okay.
Yes,
So
that is the magic of the math demo day.
Cool. I can get started with my presentation. This is just as I continue my review of Algebra 2. Last week we covered factoring polynomials using a common factor, and now we're covering factoring polynomials using structure. And so this is a pretty cool concept because it also relates to how we come to a lot of these like mathematical rules or formulas, is basically recognizing that there are certain patterns in the way that when we solve certain functions, how do they result? And we can skip those steps by saying, here's just a formula you can use or a structure you can use, which you see in the quadratic formula, but we can get into that later. Anyways, so if you haven't already, you can check out my project on factoring polynomials using a common factor, which I link in this project. But first, we'll just review what are polynomials. Essentially, it is an algebraic expression consisting of variables, coefficients, and the operation of addition, subtraction, and non-negative integer exponents of variables. So polynomials can have one or more terms. This is just one example. So a quadratic equation is a specific kind of polynomial equation where it is a second order polynomial equation in a single variable x, and with a coefficient that the first coefficient does not equal 0. And second order just means that the highest exponent is raised to the power of 2. So if, let's say, you have a polynomial where it's like 2x to the power 5 plus 3x plus 8, this would be a fifth order polynomial, because the largest exponent here is 5, right? So that's what the order of a polynomial means. The solutions of a quadratic equation, also known as roots, can be found using the quadratic formula. And so basically, if you have a quadratic equation, such as, 8x squared plus 4x plus 6, in order to solve this and find the roots, all you have to do is plug these numbers into this formula, where, for example, let me just back this up here. A would equal 8 because it's the first number here. B would equal 4, and C would equal 6, as you can see here from this equation. And then we can literally just plug these numbers into this formula, and that's how you get the roots. So this looks very complicated, but all it means is that you just plug those numbers in, and that's how you find the roots of a polynomial. So what are the roots of a polynomial? The roots of a polynomial refer to the values of a variable for which the given polynomial is equal to 0. Essentially, when the variable is equal to that root number, then the value of the polynomial is 0. So when it was talking about, when we were looking at these the terms over here, one of them was functions, where you see this f of x. Basically what this means, what f of x means, is that you have a function, and for that given function, when you input different variables represented by x, you get certain outputs. So just taking this polynomial as an example, when we input x of 4 into this polynomial and look at the value, we get 100. So f of x, or f of 4, would equal to 100 because of that. Do you see what I mean, Isla?
I think
because x is referring to this x-axis here. And when f of x, or f of this whatever value on this x-axis is equal to 4, we can see that this polynomial results in the value, y value of 100, right? So that's basically what a function is representing when we have this f of x. And this is what the roots are representing, is when f of these certain values of x, when we plug these values of x into the function, it returns 0, right? You see how the roots of this function is -2, and then this value here, which is probably around like 0.2, -0.2, and then 3, then we get the y value of 0, also known as x-intercepts. So we'll move on, because this doesn't actually this is not too relevant. I just want to cover some of these basics of like quadratics and stuff, but this might make sense later. And so when it comes to quadratic equations, there is a certain part of the equation that tells us the nature of the basically the nature of the roots, and like which direction, like where the roots are in a polynomial. And the discriminant, the term for this is the discriminant, and that's under the term under the square root. So as you can see, we have this quadratic formula here, and this would be the discriminant, the term under the square root. And what this tells us is that if the discriminant is positive, the equation has 2 distinct real roots. If the discriminant is 0, the equation has exactly 1 real root, also called a double root. And that if the discriminant is negative, the equation has 2 complex roots. And all this means is the nature of the polynomial. So for example, if the discriminant is positive, it has 2 distinct real roots, which you see this blue polynomial here, the blue line. It basically means that we have 2 of these roots that are on the line, right? If the discriminant is 0, it means there's only 1 root, a double root, which means there's only 1 root on the line. You see that? And then if the discriminant is negative, it means we don't have any roots equal to 0.
So what is a discriminant?
The discriminant is section of the quadratic under this, if we plug the numbers into this quadratic formula, this would be the discriminant. So for example, if we have a quadratic equation of 7x squared plus 2x plus 8, 7 equals A, 2 equals B, and 8 equals C, and we want to find out the discriminant, all we have to do is see B is equal to 2, right? So it would be 2 squared minus 4 times A, which is 7, times C, which is 8. And then if we solve this, times 8 is 56, times 4 would be 224. So we have minus 224, I believe that's correct. And then 2 squared, which is 4. And then we have 4 minus 224, which would equal negative 220. Because we have a negative discriminant, what does that tell us about our discriminant? It means that it has 2 complex roots, and which makes sense because I kind of just randomly made that quadratic. And so that means that the roots would be a complex number. It wouldn't be 0. You see that? So that could just tell us about the nature of this polynomial, which could be helpful in some cases. So that's what I'm discussing here.
I see.
Yeah.
I see.
So that's pretty cool, right? And how you could just know
Yeah,
that
is
just
cool.
based off the discriminant. Anyway, so now let's just cover some of these applications of quadratics and factoring polynomials, because this can be helpful in kind of seeing how this can be applied. In physics and engineering, it can be applied in projectile motion. Let's say if you're throwing a ball, right, it might follow the curve of a polynomial, in which case you could determine mathematically like where would the vertex of that polynomial be, like what is the highest point, and all of those things.
What would
right
be 0? Or like
0 might be ground level. Like let's say if you're talking about, you know, dolphins leaping in and out of the ocean, right? Like that might be the line of the ocean, like sea level, or
right.
you know,
Yeah.
there's just a lot of things that in which that could be applied. Then in economics and business, profit maximization, businesses use quadratic equations to model revenue and cost functions. Like if you raise the cost of your product, then maybe you might make more money, or it could be that less people want to buy your product, and so less, and then because of that you actually make less money even though you raise the price. Right? And so because of that, you can maximize profits by finding what is that point where you have the optimal price based off of the demand of customers, right? And so that's where you can apply quadratics, right? If you map that revenue function. So yeah, there's a bunch of others here that can be cool, but we can now move on to the actual subject of this, which is how do we factor polynomials using structure. And the reason why I covered all of this is kind of giving you basics of what quadratics are, because there are certain patterns when it comes to solving quadratic equations that can be used to more efficiently solve these problems. So there are 2 general patterns of solving quadratics. Not all quadratics. Yeah, what's up?
What does it mean to factor something?
Factor means, like, basically if you're talking about factors of numbers, like let's say you have the number 20, and then there are factors, which is basically which numbers can be multiplied by each other to get the number 20, right? So obviously 1 multiplied by 20 will get you 20.
Oh, right. I remember now.
Yeah, so that's the concept of factoring a single number, but then there's also the concept of factoring a single equation, which is basically which terms multiplied by each other will result in this equation. Just how we were talking about, whoopsies. Just how we were talking about these terms here. The terms are parts of the equation separated by your operators, right?
Yeah.
So what terms multiplied by each other will result in your equation? Or what expressions multiplied by each other will result in your equation? And so, for example, so we'll get into some examples later and it'll probably make more sense. But there are two commonly occurring patterns in quadratics equations that can help you factor your expressions more efficiently and identify the patterns that'll help you see that. And basically, there are two of these. One is if you have u and v are either constant integers or constants that we were talking about earlier, or single variable expressions, which means like you might have 3x as an example as like one of u or v, or you could have just a regular number like 8, right? And so these are just I guess like mapping general structures that you might see in quadratics. But basically these are just two dichotomies that will result in different quadratics. And so if you have a pattern of u plus v squared, so basically you have this this expression of u plus v, and then that's squared together, or u minus v squared together, it'll either result in u squared plus 2uv plus v squared, or u squared minus 2uv plus v squared. And the reason why is, let's say you have u plus v squared. This is also equal to u multiplied by u plus v multiplied by u plus v. And the reason why is because we're basically multiplying this by itself, right? This is the same thing as u plus v times, u and v look very similar. Okay, times u plus v. Basically, we're just helping us because we're having u go into both of these and we're having v go into both of these, right? And so I'm just trying to map that out in a way. This is also talking about the what's it called? The distributive property that we were talking about earlier. So if you're trying to solve an equation like this, this is basically how you map it out. Okay, so let me what's up? Yeah.
Can we use different letters? I'm getting confused.
Okay, yeah, we can. I'll use a plus b squared can be represented as a times a plus b, right, which is distributing a into both a and b, and then b times a plus b, which is then distributing b into both a and b, which we need to do if we're squaring these, right? So if we do this, then we get a times a, which equals a squared, a times b, which equals ab, then we get b times a, which also equals ab, right? Because that ba, ab, it's the same thing, right? So might as well make it easy on ourselves. And then b times b, which equals b squared, right? And then because of that, we can simplify this because ab plus ab equals 2ab, right? And then this would equal 2ab. So a squared plus 2ab plus b squared, which is what we see here, right? And so basically, if we have a quadratic where we factor it and it gives us something plus something squared, it will result in this dichotomy, and we can just swap out the terms, right? Like we don't need to go through these steps if we already know what the outcome is, right? And the good thing about this is that if we see this sort of dichotomy, we can also do it in reverse. You see? So knowing these structures can help you save a lot of time, right? If you could just recognize it and just solve it.
You use big words.
Oh, thanks. And so this is the exact same if you take A and then minus B and subtract B, right? Also, Isla, you're doing amazing because you're not supposed to be learning this in like many years. So, okay.
I can't write R.
You use big words too.
So we can do the same example if you want, but basically, if you have A minus B squared, right, then this would be A minus B
Wouldn't it be
minus B A minus B.
Wouldn't be A squared minus A B A plus
Yep, minus A times B, so it would just be
minus
AB.
A
Or
A
B A, same thing.
minus B squared.
Minus AB, because we have minus B times A. Right, so then it would be another minus AB, and then minus B times minus B would be positive B squared, right?
Oh, right.
Because the negatives cancel each other out. So then what we result in is A squared minus 2AB plus
right, that's
B
what
squared.
I was thinking.
Yeah, so these two are very similar except for this one sign change, right?
Yeah.
Okay, so now that we have these structures, this is just one of the dichotomies, right? We have two here. And then this other one is U plus V times U minus V. And so what would we get if we get equation like this? It would just be U squared plus V squared, and we'll walk through it. So if we have A plus B times A minus B, and remember, if we are recognizing this sort of structure, the A's need to be the same, right? Because it's the same variable, and the B needs to be the same. So it would, if 2 plus 3 multiplied by 4 minus 5 would not fit this dichotomy, because 2 and 4 are not the same, and 3 and 5 are not the same, right? So this is this will only work if those numbers are the same, right?
Okay.
And so now if we take this and we have A times A minus B plus B times A minus B, right? Then we would get, okay, so A times A is A squared. A times minus B is minus AB. Plus, yeah?
But wouldn't that I don't think, is that right? Because I don't think A plus B, wait.
This is A times minus B. Because we're just like the distributive property we covered last time, remember? During your presentation, right?
Yeah, but I mean, does the blue, I'm trying to figure out how the blue equals the green.
Okay, the reason why is because basically what we're trying to do is we're breaking this up, where because of this, we are taking A, instead of multiplying A plus B times A minus B, we're taking A times A minus B, and then we're taking B times A minus B. You see that? We're just taking this incrementally. And then we're taking B and then putting it into A minus B. You see that? That's why I'm writing A minus B twice, is that we need to take A, distribute it into A minus B, and then we need to take B and distribute it into A minus B.
Okay.
Because there's two components here, right? It would be really easy if we only had 3 times A minus B, right? Then we would just need to do this, right? But if we had 3 plus 4 if we couldn't simplify this, right, these are like terms, so we could obviously simplify this a minus b, we could just do 3 goes into a minus b, and then 4 goes into a minus b. And the way we could represent that is by saying 3 times a minus b plus 4 goes into a minus b, right? Because both these terms need to go into a minus b, because we need to distribute both these terms into a minus b. Does that make sense?
No.
Okay. Some of this you're kind of getting exposure
I'm just getting confused with the A's,
Okay,
the
so-
B's,
okay,
the
some of
ABs.
this you're getting exposure to it. Some of the intuition can come later, but let me just try to finish this example up.
All right.
So this green stuff does equal the blue stuff.
Okay.
As you continue to see it, it'll make more sense.
All right.
Okay, so a times a equals a squared. A times minus b equals minus ab. B plus a equals plus ab. And then b times minus b equals, it's going to be
It should be minus b squared. So the answer should be u squared minus v squared.
yeah, this is wrong. So this needs to be minus b squared. So I'll change that. All right. But as you can see here, minus ab plus ab cancels each other out, right? You're taking something, because Isla, this is basically, that's like saying minus 2 plus 2 equals 0, right? Because you have minus 2 and then you're adding 2, which gives you back to 0, right? Because you have this number line, this is 0.
Yeah,
You're
I
going
see it,
over
I see
2 and then you're going back, right?
I see it. Yeah.
Yeah, so if you have a negative of something and then you plus itself, then you're going to get back to 0.
So then is it just
Because of that, this cancels each other out, right? It doesn't mean anything.
Just a
Squared
minus b. Oh,
Yep,
wow.
there you go. So
That's very nice.
yeah, isn't it?
Yeah.
All right, so now let's apply this to some equations, and we only have 10 minutes. Jeez, right. Okay. So we want to factor the following expression. What pattern can we use? We're thinking, which dichotomy does this fall into, right? And so first, let's try to expand this out. So we have x plus 1 squared minus 4y squared, where we can take x goes into x plus 1 goes into x plus 1 minus 4y squared. We get x squared plus x plus x plus 1 minus 4y squared. And then we get x squared plus 2x plus 1 minus 4y squared. And so here is the equation that we're left with. Is x squared plus 2x plus 1 minus 4y squared. And I might have chosen an equation that doesn't fit into either of these, because in the Khan Academy there's also an option of none.
Oh
Um,
no.
So let's see here. Yeah, I'm gonna skip this one.
You can do it, Sumay, because
Which
there-
one?
4y squared is really 2y to the squared. So you can, this is x plus 1 minus 2y and squared. So
X plus 1.
2y, 4y to the 4y squared is, yeah, that's right.
Okay. This doesn't necessarily fall in because there's 3 terms here, not just 1. So it doesn't actually fall.
Okay. It's actually not correct. It should be x plus 1 minus 2y, plus 2y, and then times x plus 1 minus 2y. So it's the
yeah,
so the second
right.
the second it's
So it would be
v
the second one.
u
It would be second
times
one
u minus v.
if there was actually 3 terms in here, but there's only 2 terms. So it actually doesn't fit into any of these because there's 3 terms.
No, but your u is x plus 1. Your v
Oh, okay.
is 2y.
All right. Yeah. Okay. I get it. All right. So I'm gonna skip these two because they're this one because it's basically showcasing the same thing, but because I have 3 different types of questions here. So this one is talking about if we know the dichotomy here, which is u plus v times u minus v, then what are the factors? What are u and v, right? And so the way we can do this is just by thinking, well, because we have this plus v and minus v, it's canceling the middle part out. Just like we see up here, right? It's canceling this middle part out. And so because of this, we can know that, okay, basically we're just thinking, what is the square root of 9x squared? Because we know that it's getting multiplied by each other, right? The dichotomy of u plus v times u minus v is u squared minus v squared. So because of that, we just need to find what is u and what is v, right? And so the u here would be 3x because 3x squared equals 9x squared, right?
I'm a bit confused.
If you take 3x multiplied by 3x,
Then
it's 9x
Yeah.
squared, I think.
What?
Mommy, is that right?
Wait.
Yes.
Yeah, Isla, because basically you're taking 3 times 3, which is 9, and then x times x, which equals x squared, right? Because x squared just means x times x, right? 3 squared means 3 times 3.
Yes.
So
Yes.
then you're just taking 9x squared,
Right.
right?
Yes.
And that's one part of this problem, right?
Mhm.
So we know that it's one of these answers, right?
Oh, I see.
Yeah. And so now we just need to do v by thinking, what's the square root of 4y to the power of 6? And the thing is that y to the power of 3 times y to the power of 3 equals y to the power of 3 plus 3, given the nature of radicals and rational exponents, which we talked about earlier, which also equals y to the power of 6. So because of this, we need to find which term has y to the power of 3. And the only one, and then also we know that the square root of 4 equals 2, right? And so then the answer would then be 2y to the power of 3.
Oh, so then it's that one.
Yep, so we know the answer is this, C.
Yeah.
So u equals 3x and v equals 2y to the power of 3. And so because of that, we can easily factor 9x to the power of 2 minus 4 to y to the power of 6 by saying 3x plus 2y to the power of 3 times 3x minus 2y to the power of 3. You see? This is the equivalent of this because of this factoring, because of this quadratic structure. You see?
I think so.
All right. Well, how much time do we have left?
Not much.
Okay, well, I'll try to do this quickly. So Now we'll just take this example here. And so how do we factor this? So we know that this is going to be a dichotomy of u minus v squared. And the reason why is because if I go up here, we see u squared minus 2uv plus v squared, which we see down here, right? U squared minus 2uv plus v squared. As you continue to do this, Isla, you'll recognize the patterns. Just trust me. Just bear with me here. Okay. And so all we need to do is what is u, what is v, and the way we can do that is find the square root of this term and this term. And so the square root of this term is going to be 6c, because 6 times 6 is 36, and c times c is c squared. And then the square root of this term is 7d, because 7 times 7 is 49, and d times d is d squared. And now we know that this term equals 6c minus 7d squared. This is the same thing as this equation. And I can prove it to you. See, 6c times 6c minus 7d minus 7d, 6c minus 7d equals 6c times 6c is 36c squared, which we see over here, minus 7d times 6c is equal to minus 42dc, or cd, doesn't matter, cd. And then this is going to also equal minus 42 CD plus 49 D squared, which also equals 36 C squared minus 84, because minus 42 CD minus 42 CD is going to be minus 84 CD plus 49 D squared, which is the exact same thing as over here. So basically what we came to is that this term here is the exact same as this term. See? So that's how we can easily factor. All right, that's it. Thank you, everyone. We probably need to hop off here, but okay.
Okay.
All
Bye-bye.
right. Okay. Bye-bye.